Let's imagine a glass tube with a vacuum inside. So we have a vacuum here. Not so different from something that, for example, J.J. Thomson might have used to discover the electron. Now, suppose that there is a piece of metal in here, and maybe another piece of metal there. And suppose that we connect this to a battery. Negative pole on this side, positive pole on this side. So the negative pole is connected to this piece of metal. Positive pole is connected to this other piece of metal. I want to put an ammeter here to measure any current. Suppose that the voltage of the battery, the voltage that we would apply is, say, just a few volts. So just a small voltage. But we know that, well, it was known from such experiments that if you apply thousands of volts across these two plates, it would cause an electrical, what is called electrical discharge, or what we know today as a beam of electron that would come out from the negative plate and travel through the vacuum to the positive plate. So that's something that was known, but it would only happen if we have a very high voltage, like thousands of volts, before the electron here can actually jump out into the vacuum. Or the other way it can happen is if we heat this up, something called thermionic emission, which I shall talk about. But in this case, this is not heated, and we only have a few volts. So therefore we would not expect to see any current. Actually, there is this gap in between. Electron cannot come out of the plate, so basically it's an open circuit and no current would flow, not normally. Now suppose now that this plate here, suppose that this plate is made of say sodium metal. I'll take this as an example, sodium metal. It's normally a very reactive metal in the air, oxidizes, but in a vacuum it's fine. We'll see why later, why I want to pick this as an example. Now suppose now that I shine some light at this. I shine some green light like this. Now the green light would go through the glass tube, so that's not a problem. The green light falls on the sodium. Now the moment the green light falls on the sodium, you might actually see a small current flowing. So this is what you would actually see if you set this up. And what happens therefore must be that the light has somehow caused electrons to be emitted from this metal, or we call it the cathode, the metal plate where electrons come out. So light can actually emit electrons, can actually knock electrons out from the plate into the vacuum. And this effect is called a photoelectric effect. Let me write this out. Light is the effect where light emits, or perhaps I should say light ejects electrons from a surface. It's called a photoelectric effect. And in the early 20th century, around about 1902, Philip Lenard, he did one of the first careful measurements, experiments, using a setup like this, with these components. Probably doesn't look exactly like this, but he did a more careful study of this photoelectric effect. And what he did was to look at what happens to this current if he used different colors and different intensity of the light. So the different colors of the light, it's possible to use different colors, make different colors of light simply by just for example, we could produce a green light. So today is very easy, we can get light bulbs of different colors, but we might, for example, use white light or even sunlight coming through the window and pass it through, say, a piece of glass that has some green color. Okay. And that would only allow green light to come through. Or if you can pass it through a piece of red colored glass, and red light would come through. So in this way, it's possible to use what we might call a color filter to actually get the color that we want. So Leonard tried out different colors. Okay, so let's see what results he got. Color, and he wanted to see the current flowing through here. So let me make a table of this, of his observations. Right, now what are the possible colors in the rainbow? We can have red, we can have yellow, we can have green, we can have blue, and we can have purple or violet. Not too sure whether this is the color for violet, but that will do. So Leonard used different colors. He's shown different colors on the metal, on this metal, at the cathode, and then he checked the current and see if there's a current. And what he found was this. He found that when he used red light, there was no current. When he used yellow light, there was no current. But when he used green light, he saw current. When he used blue light, he saw current, and when he used violet light, he saw current. Now, the interesting thing here is that when he used red light and saw no current, he thought he might get some current if he used a brighter light. But turns out that no matter how bright he made it, no matter how bright a light he used, there was no current. But for these other colors like green, blue, and violet, where there was some current, he found that even if he used a very dim light, very weak and very dim light, there would always be some current, no matter how dim the light is. So that's a very strange situation, very strange observation, because we would expect that if you use a very bright light, Alright, if the light is bright enough, surely there must be enough energy to eject the electrons. If that's, assuming that it is the energy from the light that ejects the electron. So why is it that if you use certain colors like red and yellow, and no matter how strong the light is, nothing happens? The current just cannot come out. So that was something difficult to understand, and at that time people know about that light are waves. So we can call it the wave theory of light. People know that light behave as waves, but this knowledge could not help them to understand this observation. So let me write down here the important observation. Now, to summarize this observation, it would be easier, instead of talking about different colors, to talk about to write this in terms of frequency. Now, in terms of frequency, red light and yellow light have lower frequency. Green, blue, violet has higher frequency. So I've actually arranged this in the order of increasing frequency. Right. So up here the frequency is low. Now here the frequency is high. So to summarize this observation, it would be easier to talk in terms of frequency, because then I can just talk about high or low frequency. I don't have to talk about all these separate different colors of light. So the first and most obvious observation, right, is that the frequency must be above a certain threshold, a certain value, which we can call a threshold, above a certain threshold before electrons can be emitted. Okay. It must be above a threshold frequency, okay, for currents to be emitted. So that's one important observation. The next one, the next one is that below that threshold, below that frequency, whatever value it is, no current, there is no electron emitted, no matter how bright or how intense the light is, how bright the light is. Okay, and above the threshold, there is always some current, right? Some current, no matter how dim the light is, and it is actually all these 3 points that are very hard to understand from what people already know about lights at that time, particularly number 2, of course. I mean, how is it that no matter how bright the light is, nothing comes out? And this explanation is An explanation for this observation was given a few years after Leonard's observation. An explanation was offered by Albert Einstein.